What's up guys, welcome back to another video with your boy James. Today we're going to be going over my physics 1 lab regarding constant velocity. So let's go over the purpose, which is to find something with constant velocity and to try to create a computational model of that object and to then compare the two. So some fundamental principles and models that I used were Newton's first law, the momentum principle, the definition of average velocity, and the assumption that friction is negligible. And my main result is that my model and observation looks basically the same. So now let's get more in depth into the model's equations and assumptions that I used. So the first one I used was Newton's first law, which is basically about how objects stay at rest or at constant speed unless acted on by a force. So this helped me in this lab because it basically taught me that after I gave my object an impulse, I should just leave it so that it can remain at constant speed. I also use the momentum principle, which is basically how a force can cause a change in motion, as well as how that force is equal to delta p over delta t. So I use the momentum principle to derive my velocity formula right here, and the work is right here. The same thing for average velocity, so I use the definition of that to derive my position formula. I also use the assumption that friction is negligible because I kind of have to assume that, otherwise I can't really achieve constant velocity. So yeah. Now let's get into the lab. So my lab, my system is just basically the cart, which is the object I used, shown here, which is this red thing. The surroundings were basically the atmosphere and the metal track that the cart laid on, so this thing right here. And then the initial conditions were that I gave the cart an impulse, and assuming that friction is negligible, I found the velocity to be negative 0.39274 meters per second with an initial position of 0.761 meters. And I was able to find that because I recorded the cart's motion using 60 frames per second. So then I plugged that into the tracker software we were supposed to use. And then using the edge of the cart right here, I graphed where that point lied each frame. So as you can see, so all these points. So I also calculated how long each frame was. So since it's 60 frames per second, that's around 0.016 seconds per frame. So I graphed the position and the time for each frame, and then that is the blue line right there. And then I represented this in code by changing the velocity formula and replacing these variables with the computer variables. So for the velocity, I used this formula shown here, right here. And then the same thing for position, right here. And then I also updated it so that the position vector in the program and the velocity vector are the same as my observation, so right here. And so for the program, it just runs like this. So basically the same thing as my observation, which went from greater measurements, like around 80 centimeters, to the lower side, so negative velocity basically. So these graphs basically look the same. Same velocity, same initial position, same force after the impulse, and the same time that I gave them to run. And essentially there were no differences. So I think I pretty much achieved being able to accurately represent my observation in code. But some sources of error, possible sources of error, include me not being able to read the position accurately because this video is a little bit blurry. So like if I zoom in, let's say to 200, that point right there, it is a little blurry. So I could have messed up by like, I don't know, 0.1 or 0.2 centimeters. And it's also possible that each point was not accurately plotted. So in each frame, I used this point, so I just moved up, and then I did that for each frame, but it's possible that they could be a little off, and then that would make the positions a little bit off. So to answer the what if the axes were flipped question, the magnitudes of both the position and the velocity would still be the same. It would just be that the signs are flipped. So instead of being positive, they'd be negative, and instead of negative, they'd be positive. And to answer the what does it mean question, about how if it's possible to say how many pushes and pulls there are to get zero net force, I'd say yes, because there's a downwards force of gravity and an upwards force of the normal force, and these two cancel each other out. These two forces cancel each other out to give a net force of 0. Yeah, so yeah, that's basically it. Thank you for watching. Bye.